let's tackle this beam problem together, guys. So let's analyze this. We have what it looks like to be a trapezoidal load, which is a rectangle in the middle, two triangles on each side, equivalent length. We have 50 newtons hitting the beam axially. So let's solve for this. Now, in this case, what are the reactions here? We have a pin here. Let's call this B. Let's call this roller A. So this B, we're gonna have a BY, a vertical reaction, and we're gonna have a BX, which is a horizontal reaction. Let me draw it nicely here. I'm gonna assume that it's gonna face this way. We have BX. And I know the roller, we only have one reaction, so gonna get AY. That's all we have for that. So let's start by breaking this problem down. I'm going to move this right here. So I would do this by breaking each uh, area here into its force magnitude, right? So I see that I have just this rectangle here. So I would break that in, right? So I do base, which is 5, that's how long the rectangle is, times height, that's 30. So immediately I have a point load here in the middle. I call it right here. I do base times height, and I'm getting 150 newtons. Now I do this triangle next. I'm gonna do this in orange. Let me do it a little nicer, right? This area here, what is that? That's 1/2 base 5 times the height of 30. I'm getting 75. I know that it's concentrated in this area mostly, newtons, right? I'm gonna do purple for this side. And their equivalent length and equivalent magnitude in terms of how it's rising, 30 Newton meters. So I know that over here it's the same, right? It's going to be 75 newtons. Now, okay, let's figure out the locations of these values. So I know right here, if the triangle is 5 meters long, it's going to be 2/3 times 5. So immediately this value is 3.33 meters away. I'm going to do another one here, halfway. Well, if it's halfway and the whole beam is 5 plus 5 plus 5, 15 divided by 2, 7.5 meters. And then my last one, how far is it? It's about right here. And so then it's 1/3 away in terms of looking at it this way. So if I do this, place this value here, right? It's going to be here. So if I do 1/3, because if I'm trying to get the magnitude here, I'd get 1/3 of this distance this way to get the value of this distance from here, because I know that from here, at least it'll be 10 plus, it'd be 10 plus 1/3 5. So this is 1.67. So 1.67 plus 10 is the distance from that point load. So I'm getting 11.67. So now that we have all the distances and the force magnitudes, let's find out our vertical reaction. So I'm going to take the moment about A, counterclockwise positive. I'm going to do -75 times 3.33 minus 150 times 7.5 minus 75 times 11.67 plus our by times, what is this, 5, 10, 15 away. So let's do some quick math. I'm going to do -75 times 3.33 minus 150 times 7.5 minus 75 times 11.67. I'm getting negative 2,250 divided by 15. So my by reaction is equal to 150 newtons. Cool. 150 newtons. So we have that reaction. Let's do some of the forces in the y direction. Going to get negative 75 minus 150 minus 75 plus 150. Oops, sorry. Yeah, so negative 75 minus 150 from that uniform load in the middle minus the number 75. And that's all our loading vertically, right? But now we have our Vy, which is 150. Yes. Plus our Ay to get that final reaction, vertical reaction. So it's negative 75 minus 150 minus 75 plus 150. So no surprise because as you guys can see the shape, the loading is equivalent and lean and symmetrical. If you were to cut this beam in the middle, the loading will be the exact same on the other side. So we could have looked at geometry before we started the problem and assume that both reactions will be the same, given that the loading is the same on each side. But of course, we want to show our work and show that we understand how this force uh, equivalency works. So now, if you notice that there's a 50 newtons pointing at the beam, right? It's pushing the beam inward. So if you do some of the forces in the x direction, the 50 newtons is facing in the positive right direction. So I'm going to do 50. And I have my bx facing the other direction. So I'm going to do minus bx. And that's the only loading happening axially. So it must equal 0. So now if you solve for bx, it should equals 50 newtons. So now we have all our reactions for this beam. 50 newtons. And this is our beam under its loading, and this is its geometry with the triangles and the uniform load in the middle. And these are our reactions, and this beam is now in equilibrium. Okay, thanks guys.